Okay, so the next thing we're going to look at is once we've got this polar form, well, what's the point of writing a number, a complex number in polar form? Well, when we originally had this a plus bi form, if you wanted to say, let's say we wanted to raise this to the 10th power or something like that, we want to multiply it by itself 10 times, this is actually incredibly annoying to do because this requires the distributive property a plus bi, a plus bi. You have to do this 10 times, and foiling this 10 times would be incredibly tedious and time-consuming. Turns out there's going to be a really nice way to raise complex numbers to certain powers that falls out from learning how to multiply in polar form. When we multiply two complex numbers in polar form, or in Cartesian form, we have to distribute. So if you have z and w are two complex numbers, you have to do the distributive property. This is what we learned earlier. C plus di. So you would multiply a times c, a times di, bi times c, bi times di, and then use the fact that I squared is -1. Not the worst thing in the world, slightly tedious. When you divide, it's a bit more annoying because z divided by w, you end up having to multiply the top and bottom by the complex conjugate and simplify as much as possible. So division is actually kind of not trivial to do with complex numbers. When we multiply and divide in polar form, things get really, really nice. But we have to do a little bit of work to get there, to show what goes on. So I wrote two complex numbers up here in polar form. One is r and theta, like we had originally. This number looks like a p, but it's pronounced rho, R-H-O. It's a Greek symbol. Usually people like to pull out rho if r has already been taken, but you want to talk about r radius again. So rho, and then this is phi, or phi, is this symbol right here. So we got z is r cos theta plus I sine theta, and w is rho cos phi plus I sine phi. And we're going to look at what is z times w. Z times w equals, well, let's just write them all out. R cosine theta plus I sine theta times rho cosine phi plus I sine phi. That's what we're doing. We're multiplying these two complex numbers in polar form. Now, it would be nice to group the r and rho together, because those are multiplying each of these things in parentheses, and then we're going to have to do the distributive property on whatever's inside the parentheses. So let's group r and rho together first. We'll do this multiplication first, r times rho. You can multiply it in any order. And then we'll do this foiling, cos theta plus I sine theta, cos phi plus I sine phi. We're going to have to foil this. Cosine times cosine, cosine times I sine times cosine, I sine times I sine. See what we get. Okay. So our rho hanging out. Cosine theta, cosine phi. Cosine phi. What's the other part to the real part? This part's going to give us a real part. And then the last is going to give us a real part, the f and the l from foiling. Whereas the cross terms give us the imaginary parts. So cosine theta, cosine phi, that's the first real part. I sine theta, I sine phi, I squared sine theta, sine phi, like so. This is -1, so this is minus sine theta, sine phi. So that's the real part. right there. And then the imaginary numbers are going to come from I sine theta cosine phi. So we'll factor the I out. I sine theta sine phi. And cosine theta sine phi. Cosine theta sine phi. All right, let's see if that's all in there. There we go. Okay. Now, look, hideous. I told you it was going to be easier, not harder. Well, now we have to use some trigonometric knowledge we've got sitting around in our brain, rattling around up there somewhere. Because this should start ringing a little bit of bells. Cosine, cosine minus sine, sine. We've seen this before. I made a mistake here. This one should be cosine. Cosine phi. Right, because it's sine theta cosine phi. Sine theta. This right here, we have a sine cosine plus a cosine sine. What does that remind you of? What do these things remind you of? Don't they remind you of this identity? I'll write it over here. Let me turn it this way. Does it remind you of this identity? Cosine of A plus B equals cosine A cosine B minus sine A sine B. That's that angle sum identity that we spent so much time on earlier. It's just that A is theta and B is phi. So this is an angle sum. We got our rho cosine of the sum of the angles. And this one over here, sine cosine plus cosine sine, that's the sine of an angle sum. Wow. Wow. That's crazy. That's insane. The fact that these trigonometric identities popped up in complex numbers, it's just, I mean, it should be astounding to you guys that something as complex as multiplying two complex numbers together ends up boiling down to this trig identity where we add our angles and we multiply our magnitudes or our distances. So let me just break this into its two pieces. The distances of z and w, how far they are from the origin, multiply. And the angles added. Cosine of the angle of, we're going to try to sketch a picture that describes this in a second. Over here. So, here's one point Z, and here's another point W, two complex numbers. They have distances R and rho, and angles theta and phi to get there. And so the question is, where is the product in this complex plane? Where does the product end up being? I'm going to zoom in a little bit. Ah, yeah, there we go. Boom. The product is multiply R and rho together. That's how far you are out. Add the angles together. So we'll take theta, and then we'll add phi to it. So here's a length R rho and an angle that's theta plus phi. And that's right here is where Z times W is. So when you know the magnitudes of the two complex numbers and you know their angles, you can calculate where the multiplication is. And we'll find something very similar to this happens when we do division. It's almost the same thing is going to happen, except instead of adding, we're going to do subtraction. Crazy. We'll do an example next.